slide like before to introduce myself, and it's going to be really, really hard to keep up with the previous talk. It was just fantastic. And I'm not going to talk explicitly about my work. So my name is Marcello Seri. I am a mathematician. I work at the Bernoulli Institute here since 5 years. And I work on the kind of mathematics that can be used to describe why you can parallel park your cat, or why a cat that it let go would fall on her feet, which is surprisingly useful to move astronauts and satellites in space, by the way. But I don't work on the application. I work on the abstract side of it, trying to develop the language and understand what is going on. And the kind of work that I do, I try to find a way to describe it in pictures. So what I'm going to do now is just showing you lots of pictures and try to find my way around those pictures and say where mathematics enter in this thing that is in principle physics or astronomy. So the question is, how do we know that tomorrow there will be the sun rising? Does somebody have any guess? How we can guarantee that that is going to happen? Of course you can say it has happened so many times that we can expect it. Somebody can say, let's look outside, but then we need to check for the clouds first. But the point is that it's something so common that we give it for granted. But some of these abstract results in mathematics can be used to know if this is actually going to be the case, and if this is going to be the case forever, for example. And so I take it quite back. I go and think, okay, we don't know. We know that the Earth revolves around the sun, and that the revolution of the Earth on its axis is what brings nights and day. So we need to know that there is a sun and there is an Earth that goes around that. And this is kind of settled, right? Kepler described the laws of gravitation already in the 1600s, and Newton has shown that this is something that could work in the solar system, but they were looking at measurement in space on moons of Jupiter or Mars around the sun. And what was known at the time is that if you have a very heavy body, and in fact if you have two bodies, things are pretty stable. There is a small equation. This is the only equation in the talk. I don't need it. It's just to show that this whole thing is described by something very compact, and it's been well known for half a century already. And so things are very nice and stable in this case. If you look at this picture, yes, sunset is not a problem forever. But then what really happens if you take three celestial bodies and you put them in space, and then you see what the dynamics is, this is what usually happens. It's not that everything is nice and turns around, but this problem is known to be chaotic. So if I put them randomly somewhere, it's going to be a mess like is in this picture. And there is this three-body bot, if you look around, both in Twitter and bots in space, whose only job is every day picking three planets, put them randomly in space, and then show you what kind of a mess comes out of it. And this is just three. And it's actually fun. So if you wait until March, there will be a TV show on Netflix called The Three-Body Problem that is out of this trilogy of books, The Three-Body Problem, that is all around the fact that if you have three, it's going to be complicated. And yet, even if this thing is chaotic, and chaotic means that we can say what happens in a short time, but we can hardly say anything. It's like climate, or weather more than climate. Climate is much more predictable in some sense than weather. Weather, if I know what happens today and I know the state of today, with the best models we have, you can go 1 week or 2 weeks, but you can prove that you cannot do much better than that. Perhaps if you stretch it, you will go a month, but it's chaotic. Very, very tiny changes in the initial condition, this is called butterfly effect, can make absurd differences in not that long from now. Yet, a thing being chaotic doesn't mean that it's not regular. The chaotic system is chaotic because there are so many different periodic things that happen inside that when a body is moving around, it jumps between one periodic set and another, and then is changing its state, getting closer to all these periodic structures. And in this case, it's known that there are infinitely many. This is just a few of the ones with three bodies. So do we have any hope of saying anything in here? I mean, in the solar system, we have 7 planets, we have 290 moons, we have the sun. There is lots of stuff in there that can make things go wrong. So if you look at it in this way, it makes sense to ask, how do we know that the sun will rise tomorrow? And then I will take a step back and I will start from a pendulum. So if you have a necklace, you can just put it out and let it oscillate, and we'll do this. And this is a necklace as one usually see, or a pendulum. And this is a pendulum for a mathematician. So what we want to do is not looking at the symbol object here, the single one, taking it and moving, but we want to find a way to be able, why don't you move? To be able to describe all of them at once. So the picture that I have here on the left with all these circles, in fact, this contains the whole information of all possible pendulums of this type. There is no friction, there is a rigid bar, and it's oscillating. And depending on how much energy it has, so how much I kick it, it could be here, it's almost still like the previous one, or it could be here, it oscillates a bit, or it could be here, it oscillates a bit more, or it could be here and oscillates a lot more, and then if I kick it very, very hard, I can get to this part of the eye in which I go very, very close to being standing still on top, and then I move out and go up. And if I go higher, of course, I'm just rolling around. And the point is that while it's true that if I have a system and I study my little system, I can say something about the system, if I have a way to describe everything in my system at once, and I can describe what the structure of the space, so how many of these points here, fixed points are around where the system is completely still. How many curves connect these points? What do they look like? And if you can understand this picture, then you can say a lot more about your system. Because when you modify your system a bit, like you add friction, you add a planet that is pushing a bit, you add some other force or whatever, and this force is small, then you are deforming this picture a bit. And then you are destroying some parts. For example, it could be that if you are here, sometimes you jump above and sometimes you jump below, and the pendulum starts oscillating a bit and then rotating and so on. And so this is the job for the pendulum, is also the job of physicists, but the job of mathematician is forget about the original system. Let's find a way that describes all the possible state of this system and all of the systems that look like here. And then let's try to understand what can happen. And what I was saying is that if I understand this eye, then I can understand many other systems. Like if I add friction, then my pendulum, if you see, is going around, not in a random way, but it's going around all this picture of the eye. So knowing what the eye does can tell me a lot more also of the more realistic systems. Of course, I can make another change to my pendulum, and I can attach two pendula together. And in fact, in this picture, there are 20. And they are 1,000th of length. The distance between all of them is just 1,000. So they are almost all overlapping. And then I let them oscillate. And now it looks like it's fine. But if you have waiting long enough, you see this butterfly effect happening. That one thing start getting larger and larger and larger, and suddenly they all have a very different behavior. So now the big question is it true that when I have a system like this, I can still say something if I knew that I for the pendulum? And surprisingly, funnily enough, yes. If you know that your perturbation is small in some sense, the friction is little, or the mass of one of the pendula is huge compared to the others, or one is very, very short and the other is very, very long. If there is something that is much bigger, then we know that things are distorted a bit. And we can see, this is a real system actually, coming from celestial mechanics. I don't remember, I think it's what happens if you have a planet with a moon, and the moon is stretched by the planet when it's rotating, and then what happens that, I don't remember the details, but in some of these cases, this would be the resonance of the moon with the planet. So like our moon is always facing the Earth because it rotates at such a speed that it's keeping track of our rotation. That's described in this picture. But what this is telling us is that if the changes are very small, then a lot of the structure remains there. And we only need to know if we are here in the middle where everything is regular like in the pendulum, or if we are here close to these purple areas where things are getting chaotic, to know what can happen and how long will it take to happen. And if we are stable, right? If you are here in the middle and I make a little change to my system, I remain in a very regular area. So my pendulum won't do much more difference from what I was, or my planet will move in a very, very similar way. So there are especially two theorems that say that if your change is small, then a lot of the lines that you had in your eyes will stay there. And depending on how big it is, you will know how many will stay there. Which doesn't mean that things are simple. It just means that there will be still a lot of that structure present, like we saw when we were doing the distributed one, or like we see in this picture. And there is another one that say, even if you destroy a lot of them, you need to wait a lot of time before you move away from the one. So if I start very close to this one, this line here, and I'm in this system here, where that line has disappeared, it will take a long time before the evolution of my system will move away from that. And so knowing the original I will tell still a lot. And now we have to figure out how much time, and we have to figure out where we are. And we can see this already in the pendulum, where perhaps it's easier. So this is the version of the eye for the pendulum. It's a slice of the eyes of this double pendulum because it's higher dimensional, two-dimensional thing. But what happens in this picture is that if you know that you are around this purple region, then you will only move in these certain parts of the picture. And so this motion, even if it doesn't look very regular, it's very predictable in some sense. If you're on the blue one, you're kind of periodic. You keep bumping between these 5 possible oscillations. The green one is basically nothing happens, and so on. So if you know where you are in this eye, even after the system has become chaotic, you can say a lot. You can say if you are stable or unstable. So we have some hope to say what happens to our solar system. But to know if we can say anything, we need to understand what is large and what is distance in the solar system. And I think that it's easier to say with a video. It's not my video, it's done by other people. I just cut out the pieces that I need. But if I want to apply what I said to the solar system, I need to find something big, something heavy, and something distant. And this is the planets that we're used to see, but this is the actual proportional way they are. So you see most of the moons are actually as big as our planets if you take proportions right. And there are just 2 huge ones, and Uranus and Neptune are big. But even then, this is huge compared to Earth that is here, but the Sun is huger. This is really, really, really big. It's like 300,000 times the Earth. It's massively bigger. And if that wasn't enough, this is not really the distance between the Earth and the Moon. Like in picture, we see them so close to each other, but probably if they were so close, we would see the Moon as big as half of the sky. And we would have terrible troubles with the sea and with earthquakes, I think. But I'm not a physicist, so I don't know, not an astronomer even, I don't know what happens. But this is actually the actual proportional scale. So the Moon is pretty far away. And this is the closest thing we have. So when you put it in scale, this is not what this looks really like. But it's much more, if you stuck between the first 4 planets, then you will see that the Sun will start getting very, very small already. And this is just Sun to Mars. So we are already at the level of dots that are very, very distant. There is a web page where the Moon is 1 pixel. You start from the Sun, and you have to scroll through the solar system, and it takes a massive amount of time. And this is just Neptune. So Pluto would have been something like there. So planets are microscopic compared to the Sun, and they are hugely far away. So we have something that is very long, and we have something that is very heavy. And so thanks to that, basically we can say, yes, that theory, even though it's a theory on Newtonian mechanics, is not relativity, so it's not accurate for the space, but the results of that theory, the abstract result that we remain close to the eye and we remain for a long time close to the curves in the eye, that can be applied to the solar system. And they actually tell you that for a very long time, things will remain stable. And you can use it. Like this is just Sun, Earth, Moon. And if you look at the points in which the gravitational attractions are balanced, then you find these points denoted with L. And we have satellites in L1 and L2. And we put them there because basically these points are there, are stable, are using the symmetry of the system, and they are tracking the object. They put a satellite here. And with very little fuel, it remains here, and the Earth gravitation is dragging it along. James Webb is here. This one here, I don't remember the name. There is another NC something. And there are a lot of asteroids and dusts in here, and L5 and L4 that are also related to some of these meteor showers that we have in summers, for example. So this actually works very nicely. You can compute where they are with equation, with three body. This equation for Earth, Sun, and Moon are not that complicated, and you can work out this point and find where they are. So the Sun is so big and so far, and everything is so far away that this actually works remarkably well. Yet, I told you that things are good as long as you don't wait long enough. So what happens if we wait long enough? If we wait long enough, then these effects of the perturbations between the planets, then you can see them. We are talking about 190,000 years. So the scale is 300,000 years. Then you see that planets are not moving so flatly as we are used to, but start wobbling around. It's normal, it's what should be. And still they are very far separated from each other. But if you wait a few hundred millions years, in fact a few billions years, then things are getting more complicated. And each time this line crosses, it means that the orbit of one of the planets is crossing the orbit of another one. Now, the lucky thing is that the planets in this region will have disappeared by quite some time at this stage, because the age of the Sun is actually shorter than the time we need to wait before we start seeing this. So the Sun will become a massive red star and eat everything between the Earth and the Sun now. And we don't have to worry. But if we were able to wait so many years, about 10 billion years, then we could see like Mars fly by, or Mars eating the Earth, or Venus eating the Earth. So this is actually not a problem for us, and the Sun will race tomorrow. But the point is that for the theory to break, given the size of what we are looking at, it will take so long that we won't be able to not just witness it, but it can't happen because the Sun will have eaten everything by then. So this guy, Jacques Lascar, is a professor in France whose whole career was understanding the stability of the solar system, which was a question open since Kepler time, basically. And so just to say, this was a glimpse of mathematics. Since I'm here, I'm just giving an advertisement for a podcast we are doing on mathematicians and what we do, but not using any formulas. It's just for anybody that knows nothing about mathematics and is curious as what we do. We are just interviewing mathematicians around and asking, what do you do, why you do it, why you find it fun, and what it is like. So thank you very much.